Before lunch is Piotr Sulkowski, and he's going to talk, well, there it is, topological recursion and classification of multi-stranded biopolymer configurations.
So I'd like to thank the organizers for the possibility to speak.
Microphone.
Yeah.
I have a microphone.
Okay. Again, I'd like to thank the organizers for the possibility to speak here. And the purpose of my talk is twofold. So first, I would like to present some exact results on classification on certain configurations of biopolymers, in particular RNA. And on the other hand, I will find this classification using a framework of so-called topological recursion, which is some framework which arises from random matrix theory, which has been found quite recently, and is very deep, and it has many other applications. So I would like to present this as well as the underlying principle. But to start with, let me start with a specific problem of classifying, let's say, RNA chains. And to do that, let me first present this chain in the following way. So I take a backbone, which might be well, given in some complicated configuration. I just draw it as a straight line, and then each hydrogen bond I draw as an arc. So, for example, these 3 hydrogen bonds correspond to these 3 arcs, and these 5 to those arcs, and I often call those arcs chords. And of course, this is quite simplified model, but it gives some exact results, which I'm sure are interesting also in the RNA context or also DNA context and so on. So sort of warm-up problem is to count and identify all such possible configurations consistent, which consist of a given number of these chords of bonds. And this is some simplified situation, but of course, we can come across much more complicated situation. This is example of one such diagrams. And in this format, probably would like to know how many diagrams of this type exist with a given number of chords, let's say 100. And this problem has been solved some time ago. And let me just give the simplest example of this, which consists of configurations which have these chords which do not cross. So, for example, we can start with an empty configuration, just with an empty backbone, and there is certainly one such configuration. So I represent this by this one. If we take just one arc, then we also have just a single configuration. So then to this arc, I associate a letter Z, which I write here, and there is just one configuration, so I have one Z. When I have 2 arcs, I have 2 possible configurations. So first of all, I have 2 Z's. This is why I have Z square, and then these 2 configurations. And then with 3 arcs, I have 5 possible configurations. This is why I have Z cube, and then 5. And this gives me some generating function. It turns out that these numbers are so-called Catalan numbers, which are well known. In mathematics, for example, they give the number of triangulations of a given polygon. And one is able to write a generating function for this, which is just given by this formula. So in other words, if I expand this formula in Z, I get this series, and this reproduces all these diagrams. And as I say, this problem with one backbone has been solved even in cases where these chords intersect, and its answer is encoded in so-called Gaussian Hermitian matrix model. So matrix model is some theory which in some sense counts random matrices, and its properties are encoded in partition function, which is given by the following integral over a set of, in this case, Hermitian matrices. So these are matrices of size n times n. And there is some measure which, for this problem, it turns out is just Gaussian. That's why this is called Gaussian matrix model. And because this is Gaussian, then essentially this is not that difficult to solve, and people solve this model in many ways. It has many applications also in other fields, and there is a series of papers among the others by these people, but also the others who analyze this model in this context. But the real problem I'd like to talk about is a more involved one. Namely, I would like to consider an arbitrary number of backbones. So this is an example of such a configuration. Here I have two backbones and some of these bonds or arcs between them, either within one backbone, like this one, or connecting two backbones in some ways. And then I would like to find the number of configurations with a given number of backbones and arcs. And it turns out much more involved. But nonetheless, these numbers I'd like to find, I denote by this. So this letter B stands for number of backbones I specify and for the number of chords. And in fact, there is one more characteristic of such diagram, which is called genus, and this is related to a genus of a Riemann surface which one can associate to such a diagram. Namely, one can replace these backbones and these chords by, let's say, ribbons or triangles, and in this way we obtain something which is called a fat graph. So this is a fat graph of a Riemann surface with boundaries, and it's characterized by this number of, again, backbones, chords. Number of boundaries are just these boundaries of these polygons, which I would find just looking at this figure, and then genus, and all these numbers are related by this well-known Euler relation. And this is an example of diagram of genus manner. And what I'd like to do is to find generating functions for these numbers, which would give just the numbers of these configurations. And this is not that easy to do even by hand. One could try to compute them either by hand or writing computer program. It's quite complicated. This is the simplest configuration, and some analysis I will not describe it, but just to show you that it's non-trivial. In case we have just 4 backbones and genus 0, which is the simplest one, and we wonder how many diagrams with 3 chords may exist. It turns out that there are 72 of such diagrams. And then if one would ask if how many diagrams again for 4 backbones with 4 chords exist, it turns out that there are so many of these diagrams, and you can imagine that this analysis is even harder in this case. But what we would like to know is to know these numbers for arbitrary G, B, and N. And the model I will present is able to solve this problem. And for example, what I find is that these numbers come from generating function which takes the following form. And it turns out that this problem can be solved by some matrix model, which is, however, more complicated than the Hermitian one and Gaussian, which I mentioned before. And these configurations can be generated by the following random matrix theory. Again, this is integral over Hermitian matrices with some measure which is exponent of a trace of some potential. However, this potential is more complicated. In particular, it depends on 2 parameters, S and T. And then this is known that when this integral is performed and one expands this answer in larger than limit, then the answer has the following expansion. Namely, this is exponent, and then we have various powers of n, starting with n squared, which goes with term f0, and then there is f1, f2, and so on. And it turns out that this model generates this fg, which appear in this expansion. They provide generating functions of these configurations I was mentioning before, with arbitrary numbers of backbones and chords, and also arbitrary genus. And this model has been derived in this paper, and also its solution is given in this paper. And in fact, this is not that difficult to write down this model by some combinatorial analysis. But this is much more complicated to extract effectively these free energies, Fg. And this is something which can be done using this topological recursion, which I advertised. So in what follows, I would like to say a few words about this topological recursion in general, and then show the results which arise for this model for using that. So let me focus on more general situation when I would have a model of this form with arbitrary potential. And in fact, many such models are known for various other situations which have application in combinatorics, various branches of physics, mathematics, and so on. And I would like to find this expansion of this form of these free energies and this Fg. And when one has such a model, then there are two important quantities which one can consider. One quantity is so-called spectral curve, which gives the eigenvalue distribution in the limit when this n goes strictly to infinity. And one can think of this spectral curve, this is some Riemann surface of this type. One can think of this in the following form. Namely, when one considers this model and we have these matrices, and it turns out that this is quite easy to integrate everything in these matrices apart from a diagonal. But what is most interesting is the behavior of eigenvalues of these matrices. And these eigenvalues would like to reside in the minima of this potential V. So if this would be a plot of this potential, that these eigenvalues can be distributed somehow in this minima. But this measure in the Hermitian model, in fact, provides some repelling force between eigenvalues. So on one hand, they would like to go to this minima, on the other, they are being repelled. And when n goes to infinity, it turns out that these eigenvalues split cuts in the complex plane. And there is some other quantity in this model called resolvent, which can be defined nicely on the whole complex plane. And then, because of the structure of these cuts, it turns out that this resolvent provides, in fact, some Riemann surface. If we have two minima of the potential, then this Riemann surface has genus 1, and so on. But the bottom line is that this Riemann surface or the spectral curve provides is equivalent to the knowledge of this F0 term, and it provides the eigenvalue distribution for this model. And the other set of quantities is expectation values of such traces which essentially are expanded in some quantities called WGK. And then this topological recursion, which I mentioned, is some recursion which provides a solution for all this WGK. I have just 1 minute to mention that, so I'm very brief, but in fact this is the result which stems from like 3 decades of quite hard work in random matrix theory, and it has been found only quite recently. And in particular, from WG1, one can find this Fg, which we are after, these free energies. So again, to summarize very briefly, this topological recursion gives me some recursions for these correlators WGK, from which I can reconstruct Fg, and the initial condition for this recursion is the spectral curve. And now all this setup can be applied to this model I mentioned in the beginning. And then I will present some results which may seem complicated, but this is just to illustrate that this model with relatively simple potential, this was just some rational function, gives non-trivial results. So this is the spectral curve which we find, which is specified by, in particular, two numbers A and B, which would be the endpoints of one cut which we get in this model. And this A and B are given by some complicated polynomial equations which cannot be solved exactly, but they can be solved at least as a series in SNT. And using all this machinery, I can find, for example, F2 term, and this is the exact answer for that. And this sigma and delta, they are encoded they are related to A and B, which are encoded in these two parameters of the model SNT. And finally, if I know this F2, now I know that this encodes this generating function I was after. This is another example of the result for F3, so we see that they get more complicated, but I stress this is the exact answer, even though it looks complicated. So these numbers are not some random ones, but they are really quite deep. And then I expand these results. So for example, this is the result generating functions for 4 backbones with genus 2. It looks like this. So if one asks, what is the number of genus 2 with 4 backbones and 7 chords, number of such configurations is 1 for 4 times this number, and so on. And one can find in this way all possible number of these configurations. And in fact, this topological recursion provides these numbers starting from genus 2, I mean for free energy F2, F3, and so on. And F0 and F1 have to be found independently, which also can be done. And in particular, this is this answer which I mentioned in the beginning, this generating function for genus 0 and for backbones, which starts just like this. So to sum up, I presented some matrix model with the following potential, which encodes and counts some RNA or polymer configurations with arbitrary number of backbones and bonds. And I solved this using this topological recursion, which is in fact very general and interesting result in random matrix theory. And from this solution, I mean, I found this generating functions. And now one could take this model and take these results and analyze all other interesting things like asymptotics, growth of solution, and so on. And in fact, one interesting relation, let's say, to nature is that from this model, if one looks just as the one backbones, it appears that if we take longer chains, that the genus of this underlying surface should grow linearly as well. However, people looked at RNA, and most of the configurations have at most genus 1. So this is already interesting why nature chooses such RNA configurations which have very special genus from like the statistical perspective, where one would think that for a random configuration they would have much more higher genus. And finally, let me just mention a few other applications of this topological recursion. As I said, they are used also in completely different contexts. And one context which appears here quite often are knots. So let me mention that this topological recursion has also application in knot theory. Namely, one can take so-called, for a given knot, one can take so-called a polynomial of this knot, which is also some Riemann surface or algebraic curve. This is example of this curve for figure 8 knot. And one can apply this topological recursion to this curve, thus thinking of this as a spectral curve, as a matrix model. And it turns out that doing that, one reproduces some version of Jones polynomial, which is called colored Jones polynomial. And then in statistical mechanics, this topological recursion also has many other applications. It counts configurations in various combinatorial models like crystal models, dimer models, and so on. And also it has applications in mathematics. It computes generalizations of Hurwitz numbers, Catalan numbers, some Gromov-Witten invariants. And in particular, this model which I presented also has some mathematical applications. And it counts so-called number of cells in moduli spaces of Riemann surfaces. So I think this is a very rich structure with lots of applications, and hopefully it will be studied further. Thank you.
Thank you very much. Questions?
I probably missed it at the beginning, but could you maybe repeat again what is the connection between counting the backbones of RNA and this random matrix theory?
Well, I didn't explain that much just due to limited time, but the statement is that if you write this matrix integral.
Yeah, I mean, I understand that the result will be the same, but can you maybe make some hand-waving argument why there should be a connection between these two problems?
This integral, it generates various so-called fat graphs, which look similar to what I drew earlier.
So if you would introduce some diagrammatic expansion to
Exactly.
the integral, then the diagrams would look like this.
It is known that such a matrix integral with general potential, if you would write general potential with like polynomial of infinite order with arbitrary coefficients v1, v2 at x squared and so on, then it would generate all possible such an expansions with vertices associated to this v.
I see.
Yes,
So now the
like
problem
this.
is what potential to choose.
Exactly. And then I have
This kind of graph that you want to come.
So, is it possible to enumerate all links with your method, or?
You mean links in the non-theory context?
Yes.
I don't know. Of course, it would be great to have it.
Because
numbers.
somehow your presentation, like arcs going to a curve, you could always think it like a representation of a link in this sense. If the arcs are coming like this, and then you would be kind of.
Yeah, but probably even if they would be included here, then I would have probably much more configurations. Anyway, I can't say immediately. Of course.
All right, thank you very much. Let's thank Peter. I'm going to